Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and back with a new tutorial. Today we are starting with a new subject, Marine Auxiliary Systems and Deck Machinery for the 5th semester of BTech Marine Engineering course as per the syllabus of Indian Maritime University. Today we have first lecture and the topic is introduction of pumps. First of all, we will discuss about the role of a pump in a pumping system. Then we will briefly discuss about the types of pumps used in pumping systems with their characteristics. Next we will learn about the losses of head in a pumping system. Then we will learn about the Reynolds number, which distinguishes between the types of flow in pipes. Next we will learn about the Moody'S diagram through which we can find the frictional resistance in different types of flows. Lastly, we will calculate the power required for a pumping system through the following slides. Role of pumps in pumping systems. What is the purpose of a pump? For the operation of a ship, various liquids are required to be circulated through different systems. The job of movement of these liquids are performed by pumps. How are the liquids moved by the pump? Pumps impart energy to the liquids being transferred by mechanical means using moving parts. Thus, a pump is a device which creates the flow of liquids, and in doing so, the pump has to overcome the resistance offered by the system. The flow is achieved by creating pressure difference in the system. How much pressure is generated by the pump? Generation of pressure is dependent on the resistance to be overcome within the system. Power required by the pump is developed both on flow and the pressure to be raised. What is the role of a pump in a piping system? Pump divides the piping system in two parts, namely suction and delivery sides, and each side has its own characteristics. How the liquid enters in a pump? The liquid must flow to the pump on its own, either due to the head of the tank or due to the head caused by atmospheric pressure acting on the suction side of the pump. What is the maximum suction or delivery lift of a pump? The suction lift of a pump is restricted theoretically by the head caused by atmospheric pressure, which in practice is reduced by losses of head in the suction pipe. However, there is no restriction of lift on the delivery side, although losses do occur on in this side also. The pump has to overcome all the losses both in suction and delivery sides, and in addition has to create the necessary head to lift the liquid, otherwise pump stalls. Types of pumps. Pumps can be broadly split in two categories. Rotodynamic pumps. Rotodynamic pumps provide constant flow rate and discharge pressure with respect to time. Centrifugal pumps fall in this category. This can handle low viscosity liquids and are used for high flow rate at low head. The pumping action is achieved by creating the suction and inducing the liquid. Then the impeller throws the liquid by imparting the centrifugal force. As these pumps are unable to handle vapors, they may be equipped with a priming arrangement to remove air or vapors from the suction side when expected to draw liquid from a level below the pump, especially when the liquid is volatile in nature with high vapor pressure. Positive displacement pumps. These pumps can handle both high viscosity liquids and vapors. They are used for low to moderate flow rates but can provide very high head. Pumps under this category. This can be further subdivided into three classes, namely reciprocating, rotary, and combination of reciprocating and rotary type. Piston and plunger pumps fall in the category of reciprocating pumps. Gear pump, screw pump, vane pump, etc. fall in the category of rotary pumps, whereas variable delivery pump is a combination of both reciprocating and rotary pump. Pumping action is achieved by mechanical variation of chambers, thereby displacing the liquid from suction to discharge site. Losses of head in a pumping system. Loss of head in a pumping system is caused due to friction. The friction can be either between the layers of the liquid itself, which is called the viscosity, or between the liquid layer and the surrounding wall. Components of head loss. Head loss can be split in two components, which are major head loss and minor head loss. Major head loss is proportional to length of the pipeline L, is inversely proportional to the diameter of the pipeline D, and is proportional to V square by 2G. Thus, major head loss can be written as F into L by D into V square by 2G, where F is frictional factor which depends on the nature of flow, whether laminar or turbulent, given by Reynolds number. Minor head loss is equal to kV square by 2G. Minor head loss is caused by various fittings in the system such as bends, enlargements, reducers, valves, T-junctions, filters, etc. And minor head loss is equal to kV square by 2G. K is the loss coefficient compared below for some of the fittings. K is usually found experimentally, which varies with flow conditions such as geometry of the component, Reynolds number for the flow, and proximity with other fittings. Comparison of K value for some of the common 2-inch fittings are given below. Globe valve 6.5 when it is full open, foot valve has 1.5. Gate valve has K value of 0.2 when it is full open, 5.6 when it is half open, and 24 when it is quarter open. Butterfly valve has K value 0.9 when full open, 10 when it is 2/3 open, and 200 when it is 1/3 open. This is the reason why a gate or butterfly valve is always equipped on the suction side of a pump and should never be operated with throttled suction valve. 90-degree elbow has value 0.9, 45-degree elbow has 0.4, and T has 1.8. Total head loss is the sum of major head loss and minor head loss. In order to reduce head loss in the suction pipe, short length of large diameter pipe is preferred with minimum fittings. Reynolds number and types of flows. Flow of liquid in pipe can be laminar or turbulent, which is distinguished by the Reynolds number. Reynolds number Re is the ratio of inertia forces to the viscous force within the fluid, which is subjected to relative internal movement due to different fluid velocities. Mathematically, Reynolds number can be written as rho Vd by mu, where rho is the density of the fluid, V is the average velocity, D is the pipe diameter, and mu is the viscosity of fluid. Reynolds number, if it is less than 2000, it is laminar flow, and when it is more than 2000, then the flow is turbulent. Frictional factor F is equal to 64 by Re. This satisfied for laminar flow. However, there is no direct relationship for turbulent flow, which usually takes place in most of the cases and is obtained by Moody's diagram. Moody's diagram is an experimental representation between frictional F on the ordinate and Reynolds number Re on the abscissa. For laminar flow, the relationship is represented by the straight line satisfying the formula F is equal to 64 divided by Re. Dotted line shows fully turbulent flow beyond which the frictional factor does not change. For turbulent flow, various curves are plotted depending on roughness on the pipe surface. There is a small transition range where frictional factor can be approximately worked out from the two ranges. Absolute roughness of some pipe material are given below. Galvanized or cast iron pipes 0.0005. Steel pipes 0.00015 and metallic and plastic tubes 0.000005. Power required to pump the liquid. The sketch shows a pumping system where a pump takes suction from a tank and delivers the liquid to another tank at a height. Power required by the pump can be calculated from the formula PA is equal to Q into H total into W by K, where PA is power absorbed in kilowatt, Q is quantity delivered in liters per second, H total is the total head in meters, W is the density of the liquid in grams per milliliter, K is equal to 1.102, which is constant. H total is equal to head loss on suction and delivery side and can be determined from the pumping system. HPRS is equal to pressure head acting on the liquid surface at the suction. In the absence of the tank pressure, atmospheric pressure pushes the liquid to reach the pump suction. H suction is equal to vertical distance of liquid surface from the pump I. HFS is equal to loss of head on suction due to frictional resistance. HVS is the loss of head on suction due to velocity. HVAP is the loss of head due to vapor pressure. HPRD is the pressure head acting on the liquid surface at the discharge. H delivery is the vertical distance of liquid surface from pump I. HFD is the loss of head on delivery due to frictional resistance. HVD is the loss of head on delivery due to velocity. H total is the sum of HFS plus HVS plus HVAP plus minus H suction plus HFD plus HVD plus H delivery plus HPRD. Net positive suction head available is equal to H PRS plus minus H suction minus H Fs minus H Vs minus H VAT. NPSH available should be greater than NPSH required. For discharge to take place, this is important condition. NPSH available is calculated from the suction piping details, whereas NPSH given R is provided by the manufacturer. This completes the basic study of a pumping system. This book is written by me and covers all the topics as per syllabus specified by Indian Maritime University. It clarifies the concepts with simple illustrations. The book also provides answers to all the questions which have appeared in the examination conducted by Indian Maritime University. The book can help the students in preparing for the exam and also to work on ships, auxiliary systems and deck machinery safely. Hope you have liked the lecture. You can write your feedback in the comment box. If you have liked the tutorial, you may share with your friends. You may subscribe to the channel for getting notification about the new tutorials. I'll be back with a new lecture shortly. Thanks for watching till the end.